Hello, this is Anthony Schmitt here to talk about fasteners. This is a video topic number 5 for ME 3708 machine design. Now, fasteners are very important because they're the nuts and bolts that hold together all the parts in a machine or product that you design. So it's very important to have a fundamental knowledge on fasteners so you have the right cup of fasteners for the parts that make up your design. So let's get started. Now we need fasteners because they're what's called a non-permanent joint, and that's very useful when we want to make changes or if we want to redesign our product. The fasteners allow us to take apart the parts and rethink how we want to do things, as opposed to perhaps using a weld to weld two parts together. Well, then they're permanently together. It's very hard to separate them at that point. The fasteners, they create a non-permanent joint. It's only a temporary joint that can be taken apart if need be. So a very important use of fasteners is to clamp two parts together. So right here we can look at this sort of cross section of material A being clamped together with material B, and that's done so with this bolt here that's capped off with this nut. Using this diagram, we want to find the stiffness of both the bolt and the combined stiffness of the members, and so we'll get into that here shortly. One thing we need to know before we take on a problem to find perhaps the stiffness of a bolt or the stiffness of the members is the bolt specification. Now, the bolt parameters are specified differently for metric and English. And so here's an example for a metric specification. This is what you might see in a problem statement or just in a handbook for engineering. The M here indicates that it's metric. This 12 means that the nominal diameter is 12. The 1.75 means that the pitch is 1.75 millimeters. Then it's ISO. And then 4.8 is the material class, and then it says it's a hex head bolt. Here's an example for English unit specification. This 1/4 means that the nominal diameter is 1/4. We have 20 threads per inch, a length of 3/4 inches, a thread series of UNC, a class fit of 2, and it's a material grade of 5. And again, it'll say it's a hex head bolt. So now we're ready to find out the stiffness of the fastener, the bolt. And to do this, we need a few different parameters. We need LD, lowercase l sub d, which is the unthreaded length of the bolt. So that'd be from here to the threads. And that is uppercase L, which is the entire length of the bolt, excluding the head, minus the length L sub t, which is the threaded length. Then we have lowercase l sub t, which is lowercase l, which is the length of all that's being compressed. So the length from the head of the bolt to the nut that holds it together. And that is lowercase l minus L sub d, which we calculated here. Area sub d is pi d squared over 4, and that is the diameter of the bolt here. And then A sub t, which we find in table 8.1 and 8.2. And you will find that based on the nominal diameter D, and then you'll go over and find your A sub T. Once you have all those, you can calculate your fastener stiffness, K sub B, B for bolt, and it is A sub D, A sub T, times E, Young's modulus, over A sub D, lowercase l sub t, plus A sub T, lowercase l sub d. And that is your bolt stiffness. Now for member stiffness, it's a little bit more difficult to find. What you do for member stiffness, you find the combined member stiffness for each member. So we have member 1 and member 2. And what we have to do here is we have to draw our frustrum. And that is a shape that we draw in order to separate each of the stiffnesses and find the combined stiffness. So what we do is we draw a hexagon like so. That is the height of the it's not very good, but it's this height L over 2. And we divide it here. We divide it at the interface between the members. So in this case, we have 2 members. We don't have any washers. We have this frustrum here. It's frustrum 1. We have this little sliver frustrum here. That's frustrum 2. We have this frustrum 3. So to find the stiffness for each frustra, you can look at this diagram, which shows uppercase D, and then lowercase d, which is the diameter of the bolt. And we apply this in this equation, which assumes a washer face diameter of 1.5 small d, and the angle alpha is 30 degrees, which is this angle here. And these are standard values. And we get the equation 0.5774 pi e lowercase d over natural log 1.155 t, which is the thickness of the frusta, plus large d minus lowercase d times big D plus little d over 1.155 t plus big D plus little d times big D minus little d. And we calculate this for each of these frustas. So frusta 1, calculate it, frusta 2, frusta 3, and we sum them. And it's tedious, but that is how we find the member stiffness. It's combined between the 2 members in this situation. So the next important part about fasteners is mechanical stability. And one thing we can look at is an external load that is applied to the members. It'll also affect the bolt in addition to the members. These external loads that we can apply, they can cause yielding, separation, and fatigue. But the important part here is the external load affects both the bolt and the members. So before the load is applied, the bolt that is clamping the 2 members, or however many members there are, the bolt is stretched and the members are compressed. When the external load is applied to the members, the bolt is stretched more and the members are compressed less. So here's our external load P applied here, and like I said, it stretches the bolt more and also uncompresses the same amount that the bolt is stretched, and that difference is represented by delta. And delta is equal to the load on the bolt divided by the bolt stiffness. Is also equal to the load on the members divided by the member stiffness. So we have the relation load on the members is equal to the load on the bolt times the ratio of the member stiffness over the bolt stiffness. One important value is the stiffness constant, C. That's equal to the bolt stiffness over the sum of the bolt stiffness and the member stiffness. And knowing this value, we can find the resultant bolt load, and that is the stiffness constant times the load, external load, plus the preload force. We can also find the resultant member load, which is 1 minus the stiffness constant times the load minus the preload force. Knowing the yield factor of safety when you're applying this external load, in order to find that, we have to find the actual stress. Axial stress is equal to the resultant bolt load, F sub B, over A sub T, which we found in our tables earlier. Now, one thing we want to avoid is joint separation, and it's something that can happen that is very drastic with our fasteners. And what we need is the joint separation factor of safety, N sub 0. And that is equal to the preload force over the load times 1 minus the stiffness constant. And now this preload force that we're always talking about can be calculated here. And it's equal to 0.75 the proof load for non-permanent connections, or reusable fasteners, or 0.9 times the proof load for permanent connections. And the proof load is simply the A sub T that we found in our tables times S sub P, which is our proof strength.